The truth is that paradigm will break over time. We're using a lot of energy, frankly, foolishly, to do work that we don't need to do anymore because it doesn't require the same capital intensity that manufacturing once included. So I'm actually pretty hopeful that as we look to the future, as systems get more and more sophisticated, as we figure out what's next after the internet and the web, because there's got to be something better out there. I believe that. I think it's kind of broken right now. But I think as we go forward, we'll see that this will evolve and it will change the world, I believe. Infectious diseases is another area that I think is really exciting to think about and prospect. And we have some experts here. Padma works with them. Peter Hudson and his team in the life sciences. Perfect example of how computing and life sciences are coming together in ways that are very unexpected, along with physical sciences like meteorology. So I was noticing that we recently received funding from the National Science Foundation to look at the effects of global warming, i.e. transport of pathogens and changes in pathogen transport and that effect on infectious disease dynamics. Lots of different things that can be pulled together in ways that were never dreamed of before. Massive computations, absolutely massive, and massive models. And the models are not just compute forward, they're also data-driven, they're also data-intensive models. Visualization is necessary to understand these things, and whatever is beyond visualization, because there probably is something. So it's really a very exciting time, and as important as it is to be very worried about hardware and very worried about facilities and all of those sorts of very core issues, it's also an exciting time to be thinking about the science that we'll be doing, the kind of empowerment that we'll be providing other scientists who are not computationally at their core, computational scientists, I should say, and the kinds of software products and other things that will be coming out of this era in the next 10 to 15 years. I think it to be truly exciting. Now, we do have one of 3 energy hubs funded by the Department of Energy this past year. When Secretary Chu, Nobel laureate in physics, came into the DOE as Secretary of Energy, he came in with a big idea. And the big idea was to change the world by focusing on 8 key problems in energy. I won't go through all 8, but the top 3 that he wanted to work on have now been funded. The first one is being led by Caltech and Lawrence Berkeley Labs, and that is sort of putting sunlight in a bucket so you could sort of pour it into your gas tank, i.e. taking solar energy directly to fuels. We don't know how to do that, but some of the people at Caltech who are electrochemists and the like really think that they could get at the core of what's happening in photosynthesis and begin to harness those processes in ways that would be tremendously revolutionary for us. So that's a really, I would say, long-term, exciting, blue sky kind of research project. The second one's much more practical. That's being led by Oak Ridge National Laboratories, and that's computation and modeling associated with new systems for nuclear technology. Everything from the reactors themselves, making them smaller, making them safer, on through to the life cycle of nuclear and spent nuclear materials. The third one is ours, which is led by Penn State. We have a large consortium of schools. It's $129 million worth of funding for 5 years, renewable for another 5 years, and we've located this in the Navy Yard. We located it there for a number of reasons, including the fact there are lots of old buildings, and our focus is really upon renovating old buildings. And you could say, well, why not just focus on new buildings? And the reason is that if we only focused on efficiency and energy efficiency in new buildings, we really wouldn't have much of an effect on the energy economy for about 50 to 100 years. Right now, we use 40% of our energy as a nation. I think we're up around 20 quads. Is that about right? So about 8 quads or so of energy a year is on this stuff. Heating, ventilation, air conditioning, lighting. Pretty mundane stuff. And you ask ourselves, and we ask ourselves, can we do it better? And the answer is we can do it better. And we're going to be focused on that for the next 5 years. And in 10 years, the goal is to cut that 40% energy debt by half and bring it down to 20%. Well, how are we going to do that? And how are we going to do it in buildings that already exist? I mean, what do? Do you shell them? Do you start over again? Do you even need the old building? What do you do? How do you approach it? That's really the question. And guess what? We really can't build a lot of laboratories to try this. not real physical laboratories anyway, but we can build virtual laboratories. So task number one in this program is one that I'm very proud of, and that has to do with computation and visualization. Now, why computation? Obviously, from what I just said, we can run lots of models on a building and on buildings, and we can get the grids as small as we want them to be, and the structures of those computations to be as fine structured as we want them to be, or as crude as we want them to be. And we can run tens of thousands of simulations. And what we're hoping is from those simulations, we could begin to build models of the simulations. Right? So the simulations begin to substitute for the physical experiments that we would have once had to do, which we really just cannot do. So computation fills in a huge niche there. But even more than that, what I'm hoping will come out of this are models that are so simple and yet so accurate that people could use them in the field to start to make very good decisions quickly about how to renovate and redesign a building. Then there are all sorts of other issues as well that aren't so computational, that have to do with, no kidding, building materials and stuff like that, as well as issues around regulations and policies. So we have a whole task on that. But finally, we get back to sort of computation again, at what I would call sort of the esoteric end, and that's really in design. One of the things we face in this field is the fact that there's lots of technology out there already, and most of us aren't using it. Why not? Well, part of the reason is it's not very appealing. Another reason is it's expensive. Well, how do you get people to use new and expensive, cool technology? They've got to be excited about it. Design becomes incredibly important. Think of Apple. Apple used to be a computer company. What are they now? They're a design company, right? They just design stuff, and they design it better than anybody else. So one of the last tasks is really to get at the whole issue of how do we design buildings that are so compelling, that tie together energy efficiency and the functional aspects of that with the form, that people, particularly early adopters with money, will want to do this. And it becomes then an aspirational thing that other people will want to do as well, and hopefully become something of a movement. And we take a page then from Steve Jobs and the people at Apple, and hopefully bring transformation to this very important area. Anyway, so I look to the future, and I look to the past. And I think I said last year, I can remember when I was in graduate school learning how to do quantum mechanics, and some of the problems we would handle literally were PhD thesis problems that I now find in books on Mathematica, and they take up 3 pages. Some of these PhD theses can be done literally in a few minutes now. And that's only 30 years or so of my lifetime. Absolutely amazing how far we've come. We've come so far so fast that sometimes I forget, and we forget, I believe, how far we've actually moved in this field and how much farther we'll have to go. Vannevar Bush, looking to the past, said that there's an endless frontier for science, and I think that's really true. He just didn't know that it might be virtual as well as physical. So have a great meeting. Thank you very much. Glad you're here, and enjoy your time.